Welcome to G Fun Facts Online. Today, we're talking about recreating a star on Earth. For decades, humanity has pursued the dream of nuclear fusion, the same process that powers our sun. As a source of clean, virtually limitless energy, the idea is to heat a gas of hydrogen isotopes to over 100 million degrees Celsius, hotter than the core of the sun, inside donut-shaped reactors called tokamaks. At these temperatures, the gas becomes a plasma, a turbulent sea of charged particles. If we can control this plasma and fuse the atomic nuclei together, we unlock a massive amount of energy. The problem is, controlling a star in a box is one of the greatest challenges in modern science. Imagine trying to fix a complex engine while it's running at full throttle, but you can only peek at it through a tiny keyhole once every few seconds. That's essentially the challenge scientists face with fusion reactors. This superheated plasma is incredibly unstable. Tiny fluctuations can grow into massive instabilities, leading to what's called a disruption, a sudden loss of control that can extinguish the fusion reaction and even damage the multi-billion-dollar reactor. To prevent this, scientists need to see what's happening inside, in real time. But the extreme environment, intense heat, powerful magnetic fields, and a barrage of neutrons makes this almost impossible. Physical sensors have their limits. To understand this diagnostic dilemma, let's look at the tools they use. Reactors are fitted with magnetic sensors to measure the plasma's shape and position. They use lasers in a technique called Thomson scattering to determine temperature and density. Other tools measure microwave radiation or neutrons to gauge the reaction's power. Yet, despite this arsenal, the picture is frustratingly incomplete. The harsh environment means some sensors can't get close enough. Others are too slow to capture the millisecond scale changes that precede a catastrophic failure. For example, Thomson scattering is a workhorse for measuring temperature, but it typically samples data too slowly to catch the rapid instabilities that bubble up at the plasma's edge. And what happens in a future commercial power plant if a key sensor fails? The operators would be flying blind. This is the challenge, the diagnostic dilemma that has stumped fusion scientists for years. But a revolutionary approach, powered by artificial intelligence, is changing everything. It's called synthetic diagnostics. The core idea is simple but powerful. What if you could take those few scattered glimpses from the sensors we do have and use a powerful computer to fill in the rest of the picture? That's what synthetic diagnostics do. They are not physical instruments, but sophisticated computational models that generate diagnostic data. It's like reconstructing a full symphony from just a few scattered musical notes. And the master conductor of this symphony is artificial intelligence. AI, with its incredible ability to learn complex patterns from vast amounts of data, is revolutionizing our ability to see the unseen inside fusion reactors. Machine learning models can analyze decades of experimental data, learning the underlying physics of the plasma. This allows them to generate synthetic data for diagnostics that are missing, have failed, or simply aren't fast or detailed enough. Today, we're diving into how AI is not just filling in the blanks, but actively reconstructing the unseen physics of fusion plasmas, paving the way for a new era of clean energy. The AI revolution in fusion is driven by several powerful tools. Deep neural networks, which are complex webs of digital neurons, form the backbone of many synthetic diagnostic systems. There are also recurrent neural networks, designed to handle data that changes over time, making them perfect for predicting plasma behavior. We're even seeing the use of generative adversarial networks, or GANs, where two AIs compete against each other to create incredibly realistic synthetic data. And perhaps most excitingly, reinforcement learning, where an AI learns by trial and error, is being used to develop real-time plasma control systems. The true power of these AI-driven tools lies in their ability to go beyond simply guessing data and actively reconstruct physical events that were previously hidden from view. Let's look at a major breakthrough, taming something called Edge-Localized Modes, or ELMs. These are intense, violent bursts of energy that erupt from the edge of the plasma, almost like solar flares. They can be so powerful that they damage the inner walls of the reactor, which is a major roadblock for commercial fusion. For years, scientists theorized they could suppress these ELMs by applying small, precise magnetic fields. The idea was that these fields would create tiny magnetic islands at the plasma's edge, which would smooth out the pressure and prevent the explosive bursts. But there was a problem. No one could actually see these magnetic islands. The plasma edge is chaotic, and conventional diagnostics just weren't sharp enough to spot these small, fast-moving structures. Enter an AI tool called Diag2Diag, developed at Princeton University. Diag2. Diag is a deep neural network that learned the relationships between fast, high-frequency diagnostics and slower but more detailed ones, like Thomson scattering. By analyzing data from the fast sensors, Diag2Diag could reconstruct what the slower, high-resolution sensor would have seen during the gaps in its measurements. It essentially created a super-resolution video from a series of blurry snapshots. And for the first time, this AI-enhanced view provided clear, experimental evidence for the existence of those magnetic islands. The synthetic data showed the exact flattening of temperature and density profiles that theory had predicted for decades. This wasn't just a confirmation. It was a roadmap for how to effectively control one of fusion's most persistent problems. AI isn't just helping us see things, it's helping us prevent disasters before they happen. Another critical threat in a tokamak is an instability called a tearing mode. This is where magnetic field lines inside the plasma break and reconnect, causing a major loss of confinement that can lead to a full reactor shutdown. Traditionally, control systems were reactive. They would detect a tearing mode as it was forming and then try to put out the fire. But a team at the DIIID National Fusion Facility used a different approach: reinforcement learning. They trained an AI controller on a massive database of past experiments, allowing it to learn the subtle warning signs that appear long before a tearing mode becomes a problem. The results were stunning. During live experiments, the AI was able to predict the onset of a tearing mode up to 300 milliseconds in advance. That's an eternity in plasma physics. More importantly, it didn't just sound an alarm. The AI took preemptive action, adjusting the plasma's shape and the heating beams in real time to steer the plasma away from the unstable conditions altogether. This marks a monumental shift from reactive to proactive control. The AI is not just an observer, it's a pilot, actively flying the plasma and keeping it safe. And by studying the decisions the AI makes, scientists are learning new physics about how to operate reactors more efficiently. Beyond instabilities, there's the challenge of turbulence. The chaotic, swirling motion of plasma turbulence is a key factor in how well a reactor holds onto heat. Simulating this chaos from first principles is one of the most computationally demanding tasks in all of science, requiring months on the world's biggest supercomputers. Researchers are now using generative AI to create surrogate models of this turbulence. One such model, called G8, can learn the essential dynamics from a few high-fidelity simulations and then generate new turbulence data 400 times faster than the original simulation code. This allows scientists to run long-term simulations that were previously impossible, giving them new insights into how turbulence impacts reactor performance. Perhaps the most mind-blowing application of AI in this field goes beyond just analyzing fusion reactors. At Emory University, physicists used a machine learning model to uncover entirely new physical laws. They were studying dusty plasmas, ionized gases containing tiny dust particles found everywhere from Saturn's rings to wildfire smoke. By tracking the 3D motion of these particles in a lab and feeding the data into a neural network, the AI was able to precisely model the forces between the particles with over 99% accuracy. In doing so, it revealed that the interactions were more complex than previously thought, correcting long-held theoretical assumptions. This is a profound example of AI not just as a tool for analysis, but as a genuine partner in the process of scientific discovery, uncovering new principles of the universe from raw data. Of course, the application of AI in fusion research is not without its challenges. One of the biggest is the black box problem. A neural network might be incredibly accurate at making a prediction, but it can be very difficult to understand why it made that prediction. For a field where understanding the underlying physics is everything, this lack of interpretability is a major hurdle. To solve this, researchers are developing interpretable AI that can explain its reasoning, building trust, and allowing scientists to gain deeper physical insights. Another challenge is the constant need for large, high-quality datasets to train these models. Efforts are now underway to create unified, open-source databases, gathering decades of data from different experiments around the world into one place. And finally, for real-time control, the AI must be incredibly fast, making complex decisions in a matter of milliseconds. This requires highly optimized algorithms and powerful, dedicated computer hardware. Looking ahead, the integration of AI and fusion is only going to get deeper. We can expect to see foundation models pre-trained on a vast range of fusion data, which can then be fine-tuned for specific tasks. These models could be used to create comprehensive digital twins of entire fusion reactors, virtual copies where we can test new designs and control strategies safely and cheaply before implementing them in the real world. The ultimate goal, some say, is to create a fully autonomous artificial scientist, an AI that can not only control a fusion reactor, but also actively experiment and discover new ways to optimize its performance, radically accelerating the pace of discovery. The quest for fusion energy is one of the grand challenges of our time. For decades, our view into the heart of these man-made stars has been obscured. But now, thanks to the power of artificial intelligence, we are beginning to see the unseen. Synthetic diagnostics are giving us an unprecedented window into the complex, beautiful physics of fusion plasmas. From unmasking hidden magnetic structures to proactively preventing catastrophic failures, AI is not just helping us understand the challenges of fusion, it's giving us the tools to overcome them. The road to a fusion-powered future is still long, but with AI as our guide, we are navigating it with newfound clarity and purpose. We are finally learning to transcribe the symphony of the stars, and the result is a future powered by the very essence of the cosmos.